The microphone is off right there. Welcome back, guys. Now what we're going to do is start 9.2, Analyzing Rational Functions. The first little bit that we're going to go through is just rolling through some notes and explaining some of the things that are going to be going on here. And then what we'll do is we'll move into some of the examples. So 9.2, Analyzing Rational Functions. The graph of a rational function may have vertical asymptotes or horizontal asymptotes. Now, I'm just going to take a second here and sort of define what an asymptote is. At its very, very base level, a vertical asymptote is just this imaginary line that the graph cannot touch. And my pen, there we go. My pen wasn't quite working there for a second. But we have this imaginary dotted line that my graph cannot touch. Subsequently, my horizontal asymptote again would be that imaginary horizontal line that the graph can't touch. Now, technically you can cross these asymptotes, but we don't really worry about that until you get into calculus. Once you get into calculus, asymptotes will be slightly redefined in a different way. As it stands right now, they're just sort of imaginary vertical and horizontal lines that the graph can't touch. Or if you want to put it in a better way, they're these imaginary horizontal or vertical lines that the graph will approach as it moves towards infinity in some direction. Vertical asymptotes occur at the NPVs, those non-permissible values, or the values where we can't have the zero in the denominator. If you guys look, there's a little additional video talking about why we can't divide by zero. So take a look at that and it'll kind of make a bit more sense what's going on here. Now, if I look at a function and it's written in this form right here, it's not completely evident where the vertical asymptotes are going to be. So what I'll commonly do is just factor the bottom, and we see that we have two vertical asymptotes, one at x equals 2 and one at x equals negative 2. My horizontal asymptote. Horizontal asymptotes occur it's a bit different here. Now you guys will see we have at most one horizontal asymptote. That's not in general, but for every function that you're going to do in Math 30, you guys will be limited to one horizontal asymptote. As you continue on in math, get to calculus and get to some different levels of math and things like that, you can have multiple horizontal asymptotes, but as it stands right now, we're rolling with the assumption that we're only going to have one per graph. Now, with horizontal asymptotes, if I'm given a function or if I'm given a function where I have something over something, we can analyze the horizontal asymptotes by looking at the degrees of the numerator and the denominator. If the degree of the numerator, which is the top, is equal to the degree of the denominator, which is the bottom, and is in the form y equals a over b. Now, when we look at that a over b, what I do is I call those lead coefficients. And the lead coefficients are the coefficients that are on the highest degree. So if we have a degree on the top that's equal to the degree on the bottom, all that I have to do to find my horizontal asymptote is divide the lead coefficients. So if we look right here, we have that 3x minus 4, and I have the 2x minus 1. X has a degree of 1, 2x, or 3x has a degree of 1, 2x has a degree of 1. So the lead coefficients are 3 and 2. The horizontal asymptote will be y equals 3 over 2. And we will do more examples of this coming up. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote will occur at y equals 0. So if we have 3 over x, you guys will notice that 3 has a degree of 0, x has a degree of 1 is greater than 0, so the horizontal asymptote will be y equals 0. If the degree of the numerator is greater than the degree of the denominator, then there will be no horizontal asymptote. Here we have x squared minus 4 on top, which has a degree of 2, x minus 2, which has a degree of 1, so we say that no horizontal asymptote exists. Now, you guys kind of just have to take our word for this right now. When you get into calculus, you'll be able to prove this and you'll be able to show this. but it's using something called limits that you guys don't really have in your wheelhouse yet. The graph of a function does not touch or cross a vertical asymptote, but it may touch or cross a horizontal asymptote. So we can cross the horizontal asymptotes. Technically, if we're not using functions, you can cross the vertical asymptote as well. But again, as I said, as far as you guys are concerned in Math 30, you just assume that it can't touch the vertical asymptote. And we can cross the horizontal asymptote, but it's really not going to occur much within the confines of this course. Now, moving on, we also have these things called point discontinuities. And point discontinuities have another name, and the other name that they have is actually very descriptive towards what's going on. Instead of calling it a point discontinuity, I can call it a removable discontinuity. You'll commonly see point discontinuity, but removable discontinuity is an accepted name of them. Why is it called a removable discontinuity? Well, if we look at this function below, and even if you guys take this and plot it into your graphing calculator, what you'll probably notice is that you get a straight line. But if you look at it, it's irrational. How can a rational create a straight line? So I go and I factor it, and when I factor it, I notice that I have an x minus 1 on top and an x minus 1 on the bottom. So if I cancel out those x minus 1's, it leaves me with 3x minus 1. Now another very important fact about this. When we state non-permissible values, we always need to state them off the first step. We state non-permissible values off the function that we were given, not the function that we've simplified to. So at the beginning, I have the NPV where x cannot equal 1. Thus, that NPV needs to stay through until the end. So now I have the function 3x minus 1 where x cannot equal 1. So I show this by just simply putting an open dot on the graph where x equals 1. From there, if we wanted to find the y-coordinate of this, we could just look at the simplified function and substitute that 1 into the simplified function, which will give us where the point discontinuity exactly occurs. From there, we can use the numerator and the denominator of the function to find any x-intercepts, points of discontinuity, and vertical asymptotes of a rational function. A factor of only the numerator corresponds to an x-intercept, a factor of only the denominator corresponds to a vertical asymptote, and a factor of both the numerator and the denominator corresponds to a point of discontinuity. Now, when we go through the examples, I'll restate this and it'll be a lot more clear what's going on here. But for right now, we're just going to leave this as such.